going to give some tips for some of the more difficult problems on the homework, and hopefully this will be helpful. One of the most difficult problems is problem number 4 in packet number 1 about the radiator. And so in this problem, you have a radiator full of 6 gallons of water. You remove a gallon of liquid from the radiator and replace it with straight radiator fluid. So you start out with 6 gallons of water. You remove a gallon, which is all water at that point, replace it with radiator fluid, and then you have 5 gallons of water. Then I get a mouse here to kind of point out what I'm talking about. Hang on just a second. So there we go, 6, then we're down to 5. Now when you take a gallon out, it's a little trickier. So I want you to refer down to here. Each time you remove a gallon, you are removing 1/6 of the liquid in the radiator, which also means you are removing 1/6 of the water. So assuming everything's mixed up, there are only 5 gallons of water left, so you are removing 1/6 of 5 gallons. So there's 5 gallons in there. You're removing 1/6 of 5 gallons. So now you have 5/6 of 5 gallons remaining. So if you remove 1/6, 5/6 of whatever water there was in there remains. So 5/6 of 5 is 25/6, or 4 1/6 gallons. So that's how much water is left in the radiator. Now you have 25/6 gallons of water. You remove 1/6 of the liquid, so you're removing 1/6 of the 25/6. 5/6 of the 25/6 gallons of water remains, giving you 125 over 36. So each time you remove 1/6 of the water, which means that 5/6 of the water remains. And hopefully you'll be able to figure out the pattern. I also have a note down here that the answer that I used, there's a couple of possible ways to write the answer, and I show you how they're equivalent if you look at the bottom here. The next problem I want to talk about is the most difficult problem on the packet, which is problem number 7. In problem number 7, you have a ball bouncing up and down. You drop it from 12 feet. It bounces up 1/3 of the height, which is 4. Then it goes down and hits the ground again. So notice it's gone down 12, up 4, down 4, for a total of 20 feet at the second bounce. Then it goes up 1/3 of the previous height, so now we're at 4/3 feet, and then down 4/3 feet. So now you're adding all 5 of those distances together to get the total distance at the third bounce. And then you have to think, okay, now it's going to go up 1/3 of 4/3 feet, and then it's going to go up 1/3 of that. So you could figure out just by doing this what the total distance at the end of 5 bounces would be. Now the tricky part is even after understanding that, trying to get the formula for this problem is extremely hard. As a matter of fact, I tried several times last night, was too tired to figure it out. It came in this morning and finally figured it out and realized how extremely hard it was to do. You have to look for a pattern. And when you look for a pattern, it's good to write out exactly what you did, kind of step by step. So I'm just going to talk through this. I would never expect you to be able to do this completely on your own for a test. However, observing a pattern I would be able to expect you to do. So I'd like you to be able at least to get in the habit of observing patterns. So you start with 12, then you do 12 plus 2 times 1/3 of 12. That gives you the 12 plus 8, which is 20. Then you do 12 times, this one is 12 times 2 times 1/3 of 12 times 2 times 1/3 of 1/3 of 12, because now we're doing 1/3 of the previous amount. And the reason I'm writing this I'm writing it this way is to see the pattern. So if I were to look at the fourth one, it's 2 times 2 times 12 plus 2 times 1/3 of 12 plus 2 times 1/3 of 1/3 of 12, which is 1/3 squared of 12, which would make the third one 1/3 cubed of 12, and the fourth one 1/3 to the fourth of 12. And so if we go up, the 5 would be my complete pattern for the 5 bounces. And I noticed that this, except for the 12 at the beginning, this looks really like a geometric sequence. If I do the 2 times the 12, I get 24 times 1 to the third to the first, plus 24 times 1/3 squared, plus 24 times 1/3 cubed, and so forth. And so if I wanted to add these up, I need a sum of a geometric series where a sub 1 is 24 and r is 1/3. So did the formula for that. Now I wasn't quite sure if this would work out right because of the 12 and because of what n would need to be, because I'm not just adding up n equals 1, 2, 3. My first term is actually just 12 and it doesn't even fit this pattern. So I'm not sure how well this is going to work out, so I'm going to test it. So I put in n equals 1 and 2 and 3, and instead of getting 12 and 8 and what were my sums up here? Um, 12 and 20 and 68 thirds, which is what I should have gotten for my total distance at the end of each of the first, second, and third bounces. I got 36, 44, and 140 thirds. Well, the fact that I got 140 thirds was promising. 36 is 24 too big. It turns out 44 is also 24 too big. So I subtracted 24 from 140 over 3, and I got 68 thirds. So I found out that each of these numbers is 24 more than what I want them to be. So what did I do with my formula? I just took this formula up here and subtracted 24 from it. And then I did some simplifying. So I had a 12 here minus 24, so I just made this minus 12. And then I started simplifying the formula because I know the formula in the back didn't look anything like this. So 1 minus 1/3 in the denominator here gives me 2/3. And so when you divide by the 2/3, it's the same as multiplying by 3/2. So I multiplied 24 by 3/2 and got 36. And then I distributed the 36. So I have 36 minus 36 times 1/3 to the n minus 12. And then I got 24 minus 36 times 1/3 to the n. And that looks like a pretty decent looking formula. So I plugged in n equals 1, 2, and 3 and verified that I did get the first 3 numbers that I wanted to get. So my formula is good. Now it doesn't match what the formula is in the back, so here I showed how the formula in the back can be rewritten using exponent rules to give me the formula that I wrote. Whew, that was a hard one. 1F is kind of backing up. Just in case you had trouble with just remembering exponent rules, to find r, to figure out what r is, I know that the first term times r gives me the second term, and the second term times r gives me the third term. So r is the second divided by the first term, or the third divided by the second term, and so forth. When you divide by two numbers with the same base raised to an exponent, you just subtract the exponent. So if you look here and see how I subtracted exponents, you see how I got r. Moving ahead to problem number 9. Number 9, you're using the term formula for an arithmetic sequence. And this is the term formula, and you look and see what do you know. You're given a sub 1, you're given d, and a sub n is the term in the sequence. So you actually plug in 26,891 for a sub n. What you don't know is n. If you solve for n and n turns out to be an integer, a whole number like 1, 2, 3, 4, 5, or something like that, rather than 12 and a half, then you know that 26,891 is a term in the sequence. And you can do the same thing for number 10. Number 18. I wanted to explain kind of the given information on number 18. In number 18, you see that in the first example right here, this first line, this is an example of what happens if I were to deposit $100 in an account and not ever deposit anything more, just leave it in there. And it's earning 12% interest. And the interest is compounded every month, which means they add interest to the account every month, not just at the end of the year. So since there's 12% interest for the whole year, they're going to add 1% per month. So the first month, it's $100 times 1.01. That's the $100 plus 1% of the $100. So this is basically multiplying 100 by 101%, which makes it a bigger number than you started with. So if I were looking at month 1 in this first example down here, I would have $100. And then in month 2, I'd have $101. And this was I got that by doing $100 times 1.01. In month 3, I take the previous amount times 1.01. So I would have $101 times 1.01, which is the same thing as $100 times 1.01, and then that whole thing times 1.01 again. That's where you get the $100 times 1.01 squared. So in the third month, that's why we have 100 times 1.01 squared. So that's going to give me the total amount of money in the account after the interest has been added at the end of 3 months. This, and then at the end of the fourth month, or maybe at the beginning. I'm not sure when the end of interest is, if it's at the beginning of the month or the end, and so forth. So the fifth, if I left the money in for 5 months, this is how much money I would have. 100 times 1.01 to the fourth. That would be the total amount of money in the account at the end of 5 months. Now, that is not the best way to make money. The best way is to keep depositing more money into the account, not just deposit $100 and leave it. So the second example talks about here if I make regular $100 deposits each month. So notice what happens. The first month I have the $100. The second month I have the $100 plus interest and another $100 that I put in. The third month I have the first $100 that's earned interest twice, the second $100 that I put in the second month that's earned interest once, plus the new $100 I put in. And that keeps going on. So when you get in Part A, when they say, explain why the amount in the IRA at the fifth month is the fifth partial sum of a geometric series, you can see that we have a geometric series here where 100 is the first term and 1.01 is R, and it just, you keep raising the exponent each time. So this is like 5 terms. And all of that money is in the account because I've been putting money in for 5 months, and each month has a different amount of interest because some amounts have been in longer than the other. So this tells me the total amount at the end of 5 months if I put in $100 each month. If I continue the regular 100 monthly deposit, so I'm still talking about the second example, how much will be in the IRA at the end of 10 years? Well, how many months are in 10 years? Do the same pattern. How many months would it take before the total first exceeds 100,000? Okay. Well, this is going to be the sum of it. For Part B, and C, we're talking about the sum of a geometric sequence. So S sub n is equal to A sub 1 times 1 minus R to the n over 1 minus R. In Part B, you know A sub 1 and R. In Part, and you're just finding the sum. Find the sum. In Part C, you're told that the sum, S sub n, is equal to $100,000, and you want to find n. And notice that n right here is an exponent, so you're going to need to use logs. Use logs. So you're going to substitute 100,000 for S sub n. A sub 1 is still your $100. R is 1.01. And then you need to solve it for n. So that is the process for Part C. Now when you get to number 19, in 19 Part A, let me get this up on here. 19 Part A asks you, and actually I think I'm going to pause and load this on here and then start recording again, so hang on. I'm back. Okay, I have the problem up here now. Suppose that money is invested in a savings account at 6% annual interest compounded monthly. Because the interest rate is 0.5%. That's 0.005, not 0.05. Be careful about that. The accounts and the amount each month form a geometric sequence with a common ratio 1.005. Find the amount you would have to invest now to have $10,000 at the end of 10 years. Okay, Part A is like the first line in number 18. In other words, you're not adding money every month. You just start with an amount and you just leave it there and let it grow for 10 years or 120 months. Okay, so basically you're wanting to know the A sub 1 if your S sub n is equal to 10,000, you want to know what a sub 1 is. And actually, no, it's not S sub n. There's my problem. Because I'm not doing a sum. I just want to find the term. So if you go back to number 18, you'll know that the total amount is just a term in a geometric series. If you're adding every month, the total amount is a sum of a geometric series. So here in part A, the trick is, and I think this is what I did wrong the first time I did it, you're looking at a sub n equals a sub 1 times r to the n minus 1, and you're trying to find a sub 1. In part B, though, you're saying you're investing X dollars a month into this account, the total at the end of each month. This is like the second example in number 18. And this is where you're saying S sub n is equal to a sub 1 over 1 minus r to the n over 1 minus r. And you know that this is 10,000. Here's my 10,000. And I'm trying to find a sub 1 again. Now, it would make sense that if I only put in one amount at the beginning and I never put any more, I'd have to put in more in part A to get to 10,000 at the end of 10 years than I would for B, because in B I'm adding that amount every month, so it'll be a much smaller amount. Okay, so that's what you're looking at in number 19. The next one I want to talk about is number 24, because I only gave you the answers to answer to A in the back. So I want to talk a little bit about B. The trick on B is if you look at that, you'll see that B is not either arithmetic or geometric, but it does have a definite pattern. And so to find a pattern, when you're not sure what the pattern is, what I suggest you do is you list the terms. The terms are the a sub n's. Those are the terms. 1/2, 1/3, 1/4, 1/5, 1/6. Then you number them n. So n equals 1, 2, 3, 4, 5. Notice then I want to know what is it if n is just n? What if I don't know what n is? How would I write a formula? So think about the relationship between the number in the term, the numbers in the term, a 1 over 2, and the number 1. 1 over 3 goes with term 2. 1 over 4 goes with term 3. 1 over 5 goes with term 4. 1 over 6 goes with term 5. So if I get to term number 10, what would it be? Term number 10 would be 1 over 11. So what would term number n be? 1 over what? N plus 1. Okay, so my rule is just that for every n, the term is 1 over n plus 1. So how do I write that as a sum? Well, I write my sum. I figure out how many terms I need. Notice there's a dot, dot, dot at the end of this. That means it goes on forever. So I start with n equals 1 and I end with n equals infinity, because I'm not ending this sequence. It's going, or the series, it's going on and on. How do I make the rule for n? I put 1 over n plus 1, and that allows me then to generate the sequence. So if I let n equals 1, I get 1 over 2. If I let n equal 2, I get 1 over 3. If I let n equals 3, I get 1 over 4, and so forth. So that is how you write B. For C and for A is, I think you realize that's arithmetic. If you look at C, hopefully you recognize that C is geometric. So you need to think, what is a sub 1? What is r? And write the formula for an arithmetic sequence. Now, and I think I wrote it wrong in here, but just so what you should have is n equals 1 to what? How many terms do you have? And then inside the summation formula, then you should have how you get the terms of a geometric sequence. So I'm going to leave that one to you. That is all the farther I got with going through and picking out the harder problems. So if we run into some other problems later on, then I will add a little video about some of those problems, but this should hopefully help you with most of the difficult ones that you've encountered in this packet.